Hello, students. Allow us to introduce a new quantity called magnetic flux. Chapter 28, Section 1 in Tipler and Mosca, Edition 6. Anyway, here's what we have. We've got a magnetic field B. We've got a magnetic field B oriented into the page. This is our magnetic field. And well, look, we got this coil slash loop. Loop. And you'll notice in this case there is if we think, let's see. This is a loop it's a two-dimensional form as opposed to a three-dimensional surface. And in this two-dimensional form, there are magnetic field vectors that, quote, poke through or go through the loop, and thus we define a case in which, or we define this quantity magnetic flux, phi magnetic, let's say, that is a product of magnetic field and area, where the area is this area here. Sure, area of the enclosed loop. Now, in this case, can you tell which, so the area is now, or this loop is now oriented perpendicular to the plane of the page, and so none of these magnetic field lines poke through the loop. In this case, the flux is 0, which suggests that there's a special relationship between or when there is flux and when there isn't. Or, well, okay, so what we really have to have in general, magnetic flux, we can write it in one of a couple of ways. It's B. We need components of B that are perpendicular to A. Well, A apparently is a vector. Or we need components of an area vector that are parallel to a magnetic field vector. Well, this area vector, just so that there's an area vector that has a magnitude A and points in the n hat direction, the normal hat. This is n hat normal to, which means perpendicular, normal to surface created by a loop, or any form you want. So in this case, this area vector, well, why don't we say the area vector happens to point into the page also? Here we'll say this area vector, or the area vector or the n hat vector points that way. So, well, for any number of these reasons, maybe you may recognize that there's this quantity called flux that is a scalar, but is the scalar product of B and A, the dot, or aka the dot product. All right, and dot products only evaluate to a non-zero answer if there are components of one vector parallel to another, and therefore vice versa. What's it measured in? Gosh, apparently Tesla meters squared? Sure. Is there a different name for that? I don't know. Okay, good, fine. All right. Here's a case where we've got a enclosed, well, it's not a loop, it happens to be a rectangle, and we've got a field you can see that varies along, let's call that the j hat direction. So maybe there's how about a hypothetical expression for B? Let's say that that B varies with y vector as, I don't know, how about B naught, how about B naught y in the apparently inward direction, right? So we've got a spatial dependence of magnetic field with position, specifically position along this positive j hat direction. And so, well, if we want the total flux here, what we've got to do is add up lots of little fluxes, because what there are is, well, there's not a field in here, and there's an average value of the field. Let's do this instead so it's not so easy to find average value of the field. Notice I changed this to a quadratic function. If it was a linear function, we could just take the value of the field in the middle, because that is the average of the linear function here. Anyway, so what I'm trying to get at is, well, there are constant values of the field, say, within this tiny little area. This thing is a little tiny area right there, and that little area has some spatial dimensions. Why don't we call this? Let's call this. How about x? And well, this apparently is a little tiny y. Okay, so if we're going to add up lots of little fluxes, we can say, well, this is b dA. It's really b dot dA. But if we choose our area vector to also be into the page, then this simplifies to a plain old product b dA, and we have, well, we've got our function. I really should say b as a function of y, and our function is b naught y squared, and our dA is x dy, and yada yada yada. Okay, but sometimes there are cases that you'll see soon enough where cases where fields are not constant, like the field near a current carrier varies axially, we call that, as a inversely with r. Yeah. So there are cases in which there's intellectual value in finding flux where fields are non-constant. Okay. But now all this, the b naught and the x are constants, and we integrate with respect to y dot dot dot. Just be aware of that. All right. Okay. Great. There's this quantity called magnetic flux. Hooray. Well, there's also a quantity called electric flux, and people say, well, yeah, but what is it? Yeah, who cares? That's electric flux is EDA, right? Well, here we've got BDA, and what is it? It's nothing other than its own definition. But what's it for? Well, it's for something. It can be for something. And we'll talk about what we call Faraday's law. So let's take a case like this. We've got look, this green thing here is a conductor. It's a hunk of metal. All right, it's a bar, and they slide it along. So these black things are wires, and there's a resistor, and wires. So we've got a conducting loop with there's nothing's going to happen right now. Well, unless we slide this conducting green rod across these rails. Well, what happens? Well, let's take let's consider a hypothetical free positive charge. A free positive charge that is moved this way to your right at a speed v. So I go fingers to the right in an inward magnetic field. There's going to be a magnetic force exerted on that charge that points upward. So a force FB is exerted on charges, all the charges in there, on charges Q. And let's say those charges are displaced through distance L. Here's that distance L. Well, that means that there's this FB times L. And of course, times distance means there's work done on the charges. Now this we can express as QVB. That's our magnetic force, okay, times L, is the work done on the charges, on each charge that's displaced distance L. Well, we've discussed this idea of the work done per unit charge as a charge is moved through an electric field, and that is defined to be potential difference. So what happens when we move this, what happens when we move this bar, we move this green rod this away like that, what we do is we create a potential difference between the ends of the rod. And the rod, in effect, becomes, well, it's not a battery, but it becomes a source of potential difference. Now notice that these Q's go away. And so what we get, I'm just going to switch sides, is this delta V, we call this, aka an induced EMF. And we use an epsilon. Now, EMF stands for electromotive force, except potential difference is not force. But it seems, potential difference seems like that which would push charges around. So I guess that's the origin of that nomenclature. But it's not a force. It's a potential difference. All right, so this EMF, or this induced EMF, which is this potential difference, is this stuff, V, B, L. So when you slide a conductor through through a magnetic field, and when you slide it across the magnetic field, I'll say, right, we've got to slide it in such a way that there can be forces exerted on charges. Right, what you get is you basically turn that conductor into it's kind of like turning it into a battery. And so what really happens is, yes, there actually is a force exerted on these charges that pushes them like this, and what we get is we'll get an induced current in this circuit. And if we say this resistor has a resistance R, okay, well that means there's a current induced. Well, I induced will follow Ohm's law. So E over R, and we could call it VBL over R. Fair? Okay. Well, something else happens. So yes, all these things happen. That's good. We don't need to make it smaller. But let's do this. Maybe we'll call this like whatever. So what else happens? Well, let's try to connect to what we just said. What else happens as we take this rod and slide it from here over to here? Well, guess what? We've gone from a situation in which there was, well, really a flux in that amount of area to a flux now in what color? Black, sure, red, green. How about this? Yes, now there's a flux in this area. So what we've done is, what happens? Okay, how about this? Number one. All right, one, that stuff. Two is that magnetic flux changes. And it changes because we can say there's a delta phi that's equal to the change in this B times A dot product. But again, because let's define, how about we define area vectors for these things to be into the page, just like the B is into the page, so therefore the scalar dot product of those B and A vectors just becomes BA. And notice also, guys, that I notice I didn't include this part of the loop because there apparently is no field in that part of the loop somehow. So it's only the part of the loop that actually has some field in it. So I kind of lucked out with that diagram. Anywho, so yes, there's a change in this quantity, and it's not because magnetic field changes, but it's because the area of our loop changes. And then the question is, how much does area of our loop change? Well, this part, oh boy, this part is the delta A. And it's got dimension L, and how about, oh boy, how about we call this, I don't want to call it X because that looks like this. Let's call this D. So that delta A, okay, delta phi is B, L, D. Yeah, D. Look, these are, it looks like, oh, wait, how about, what if we looked not at simply the change in flux, but the rate of change of flux? Well, what do you recognize? That distance in the amount of time that it took that flux to change is the speed of that rod. So this delta phi, this rate of change of magnetic flux, is BLV slash, well, how about this? How about B delta T? How about VBL, like we had here? And thus, this is called Faraday's law. Faraday's law says that when magnetic flux changes, the rate of change of that flux is equivalent to the induced EMF. And there's a negative in there that will become, the reasons for which will become clearer later. It has to do with the direction of the induced, or the polarity of the induced EMF. Yeah? So there are lots of situations in which we will show that magnetic flux changes. This is one, and flux changes because originally there was an area bounded by a loop in which there was a field, so there's magnetic flux. And as we slid our bar this way, now we have a larger area with that same field in it, and so there's a change in flux. And so we're able to get to a result that looks like this one by manipulating things a little bit differently, but they say the same thing. Okay? And they give us two different ways to talk about E induced in a specific case where there is a wire of length L moving at a speed V through a field B. That's how much induced EMF there is. In general, in every case, when there is a change of flux, the rate of change of that flux is equivalent in magnitude to the induced EMF per Faraday's law. Thank you.